start recording, then that makes it official. So welcome back.
This one was the when I was in the language program. He was the student there, and I didn't see him for ages.
Oh,
Yeah,
so it's like a
absolutely.
family reunion over here.
Oh, really?
Family reunion.
Yeah, well, the academic families, right? That's what we're
Yeah.
building here. It's a different kind of family, but it's an important group nonetheless, so good for that. Let's see, I sent out an email yesterday letting folks know that the online homework system is ready. I made a video that lasts about 7 minutes to demonstrate it, so that's the upper limit on how long this could possibly take you. Michael just let me know I have a typo in one of the answer choices. My office hours on Wednesday start at 3, not 3:30. But the other choices were completely incorrect, so hopefully you did not fall for those. I'm not having office hours on Friday and Saturday nights or at 3 in the morning. It's just not happening. Although, if you don't want anyone to come, those would be probably pretty good strategies.
Unfortunately, you'd have to make yourself available,
This is also true.
and I wouldn't want to do that.
Yeah, no. And so if you have any questions about that, let me know. Have folks given it a try? Yeah. Any problems? No? Self-explanatory? Yeah, the one catch is to make sure that after you hit submit, that you re-enter your ID number and hit submit again. I do that to keep people from submitting accidentally, but there's always at least 1 or 2 instances in the semester where somebody forgets that second step, and so then their answers are late because they forgot to actually submit. And they are like, can you please fix it? I do, actually. I usually download like the database every day or every other day as people are working on it, just in case. So I can tell if that person had been working on it already or whether they actually did stay up all night and finish it. That doesn't record the time of submission, just the date. So if that happens, let me know. I'll fix it. That's the point of that story. I also posted new materials for example 2. So for the examples, there's 2 files that you will need to download. This one is a PDF. That's the annotated syntax and output that we'll walk through together. And then the source files that created it are also available in a zip folder. So you would start with the source files when you start working on homework. That way you don't have to try and type from the PDF. Like, it'll be easier to copy and modify things if you have the source files. And it will usually have a data set included, but if it's real data, then I'll note that it can't be included. So I think example 4, for instance, is real data. So I don't include that, just the syntax now. So. And you probably already saw a link to the lecture from last time. So that's where these videos will be. And I try to note what we covered in terms of the material. That way you can know which video to refer back to if you're looking for something specific. Next week, no office hours on Monday. That is a holiday for everybody. But then after that, we'll go back to normal. I put the due date for homework 0 on Monday, even though it's a holiday. You don't get late points, so just, sometime within the next week or so, if you could give it a try. If you haven't, that way I can make sure everybody has their access before we do stuff for real. Any questions? Cool, all right. Then let's jump back into lecture 1. What are we talking about in this class? Big picture question.
Multi-level models.
Multi-level models. What is a multi-level model? What makes it different than a single level model? Do we know that? Yeah, multiple levels because each level reflects a dimension of sampling. That's the idea. So in standard linear regression, you're expecting that your sample is independent, that the people in the sample are no more related to each other in any pocket of the sample than others. Like, people are just separate. In these models, we know that's not going to be the case. Like, we have people who are nested in schools or patients who are nested in doctors, that kind of thing. So we have differences across schools, for instance. We have differences across students. Each of those is a level in the model, and each of those has a source of variability. So that's the big thing that makes this different here. Jump back into slide 15. When we talk about what's in the model with respect to predictor variables of some outcome, that's going to function very much like what you're used to. These are fixed effects. The novel part of multi-level models is that we're going to have to start making choices based on empirical data for what we want to put in the other side of the model, which I refer to as the model for the variance. And this is how the residuals are distributed and related. So we have an E at the end of a traditional linear model equation for differences between people. We're going to pick up some new letters. They're actually going to be U's for what's known as a random effect, and that's the same kind of idea. It's differences across the level 2 units as opposed to differences across the level 1 units. That's where we're headed. So, and as a tie-in, I note that a random effect is the same thing as a latent variable. So MLM and SEM have quite a bit of overlap, which is useful once you get to models that you need at the intersection, such as multi-level measurement models, for instance. So we went over this at the end. Should I assume that we don't have perfect recall of notation? Is that fair? Yeah, okay, let's do that. So I just wanted to be a little more concrete as to what the difference looks like. So if I have an empty model, I don't think you ever need to do this in life, but I do this pedagogically when I teach regression because this is the starting point. If you don't know anything else about a person, your best guess for their outcome is the outcome's mean. Cool. E then is all the reasons why people differ from the mean. So the variance across people in E is the same thing as the variance across people in Y. That's the upper limit for how much variability the model can potentially explain. Cool. So here's words. What we're moving to is something that's going to start like this instead. So the first thing I note is the change in the subscripts. If this semester in clustered data, I'm having P for person at level 1 and C for cluster at level 2. And I'm going to keep that consistent across the semester. You might want to be more specific as to what kind of person you have. It gets tricky if they all start with the same letter. Like if you have students nested in schools, you can't use S for both. Kids, pupils, take your pick. But PC is what we're doing here. So we still have a beta 0, meaning we still have a mean, because that's still our best guess for anyone's outcome. But now we're essentially splitting what we used to think of as one source of variability into two. Because people differ from each other. But part of the reason why they differ from each other could be which cluster they belong to. So we're going to split this into two levels of variance, or two piles of variance. U0, that is going to be called a random intercept. It is how far off from the sample mean your cluster's mean is. So beta 0 becomes the mean of the means, which is not the same thing as the mean if the clusters are unequally sized. We'll see that in the first example. U0 then is how far off. So U's have a mean of 0 and some kind of estimated variance, and the notation we'll use for that, this is tau squared as variance at the upper levels of the model. And as a convention, I always put what it is the variance over as a subscript. So it is the variance of U0 specifically. So this is across clusters. Note there's no P here. Each cluster gets their own of this, but everybody from the same cluster shares whatever this is. So if my cluster is doing better than other clusters, U0 will be positive. If I'm from a cluster that's less good, it will be negative. So that gets us to what the cluster mean would be from these two sources. Then E steps in to do the rest. So then E is how far off of your cluster mean is each individual person. So if I'm higher than my group, my E is positive. If I'm lower than my group, my E is negative. And E's also always have a mean of 0 because the mean is taken by these two things instead. So E variance is going to be sigma squared sub E. And this is notation that is mostly followed in the textbooks. You will sometimes see U as a like the letter U, like I'm using here. Sometimes it's a Greek letter that looks like a little U. I do this one because the Greek letter sometimes gets confused from U, and I don't want to confuse people with that. So my notation is based on what's in textbooks that I use and what I can reliably draw on the blackboard with a marker. Those are my two standards. So that leaves out a lot of the Greek letters for the latter. But this is the main idea here. We're going to still worry about putting in predictors and things like normal, and we'll talk about what they mean. But the question is, what are the predictors for? There are two different kinds of variability represented in the model. One is, why don't all clusters have the same mean? That's going to be the variability across the U's. And that can be predicted by cluster things. Then there is, why doesn't everybody have the same score if they're from the same cluster? and that's going to be predicted by people things. So remember our friend R square from linear regression?
Mm-hmm.
It was nice. We had one. It worked like it was supposed to. Yeah, bye-bye. Why are you waving bye-bye?
Won't work.
Well,
Well, there could be an R for each individual.
exactly. So R square is complex in these models because you're trying to define out of what.
Mhm.
So a natural way to go about it, and one that you will see from me repeatedly, is to think of each of these as their own sources of variability and say, of the U variance, how much did the model explain? So like, I got 30% of this one and maybe 10% of that one. And then I would have 2 R squares, one for each pile. That's one way people talk about it. There is also total R square, which is the same thing as it is in linear regression, where that's sort of aggregating the piles back together. You can do that too. And there's a whole literature on this. There's many, many choices. Those are the two that I find the most useful. I'll show you in our package an example too that also has another way of computing it that keeps it from going negative in practice. So, but at the end of this process though, we are saying that the E's are independent, just like they're supposed to be up here. Because U0, the random intercept across clusters, is supposed to have captured all the reasons why the E's would have been related. That's an assumption. There may be other reasons which would require us to make the model more complicated. But this is your very first little multi-level model. Just 3 things in it. The notation gets a little more complicated, but I figured we could just start here as something. Cool. By the way, I'm using color quite deliberately in the slides. So in this case, red things are fixed effects and blue things are terms that relate to the model for the variance. All right, so here's my sales pitch. Are we ready for that, or does anyone have questions or comments?
One question.
Yeah.
And I think I saw it, maybe you alluded to it. So every level will have its own variance, correct?
Every level will have its own variance for the upper levels for sure.
Okay.
For the lower levels, it depends on what conditional distribution you're using at level 1. If you're using normal, then yes, like that's the assumption here.
Mm-hmm.
But if you're using a binary distribution, there actually is no estimated variance at level 1 in that case. It still exists, but
What
you
about
can't
level
quantify
2?
it. At level 2, you can.
Okay.
U's are assumed to be multivariate normal across the sampling dimension that they represent.
Okay. Thank you.
Sure. And notation, sometimes you would use U's for 2 and 3, sometimes you'd switch letters. It varies by, whatever.
Yeah.
Yep. Thanks for the question. Other questions or comments? All right. So, what can MLM do for you? Number 1, model dependency. So, dependency is one of those words that makes it sound like there's a problem. Like, oh, I have dependent data, I gotta fix it somehow. In some research settings, dependency is the point. Like if you're interested in measuring, students and their contextual effects, like you need students to be related to each other so that you can examine those things. So the word dependency just means that the residuals from the same sampling unit have some kind of source of correlation that we need to build into the model. Dependency means correlation. So we say independent data if the E's are expected to be uncorrelated across people. We say dependent data if they're expected to be correlated. So we can handle this by introducing new sources of variability. So let me go back to the equation here. So by introducing this U, you are building in a constant source of correlation for the people that come from the same cluster. You're allowing this correlation because you're allowing them this constant mean shift. So the tricky part then is trying to figure out all the different ways how residuals might be related to each other, might be dependent. So you can have nested designs. So time within person, after you control for which occasion is which, for instance, would be a nested example. Persons and clusters, that's the focus here. Schools and districts. Can you think of any others where the nesting is clear and ambiguous? Vladimir, give me another one.
Patients in clinics.
Patients in clinics, I like that. How about children and families? Partners in a relationship? Yeah, lots of examples in life. If you have a sampling design that you can't figure out what should be level 1 and what should be level 2, it's not nested, it's crossed. That's how you know. So I got into this sort of by accident. In graduate school, and I think you'll hear this story later in the semester if we have time, I was friends with somebody who paper got rejected from a journal. And they explained that it was because their F2 ANOVA wasn't significant. And I was like, what's an F2 ANOVA? I've never heard of this. Well, in psycholinguistics, which is where this person was from, they have these research designs where people respond as quickly as they can to words and non-words. And one type of analysis essentially aggregates over the words and looks at differences across people. That's called an F1. Another one does the opposite. It aggregates over people and looks at differences across the items, and that's called an F2. And at the time, there was like a rule that both had to be significant or your effects weren't real enough. Well, at the time I was learning multi-level models, and I was like, well, wait, like aren't items nested in persons, and couldn't we put this into a multi-level model so you don't have to do separate analyses, and can't I change the world with this? And it turns out that no, items are not nested in people. They're crossed. Because you could also say people are nested in items. So what you really have is like a 2x2 of item responses and people, and it's crossed. So in that case, you would actually have 2 different level 2 sets of views. You would have responses nested in people, because some people are faster on this task on average. Responses nested in items, because some items are responded to more quickly on average. And what is left at level 1 is like the unique person by item interaction. Why did this person do differently on this item after controlling for which item it was and which person it was? So in that case, the design that I was thinking of was only 1 level 2 unit and not 2. Anytime you're doing a reliability assessment where you have targets and raters, that kind of stuff, like you would want to control for which target is which rater is which, and if you're doing it repeatedly over time, then you potentially have interactions that you can control for as well, so it gets kind of ugly real quick. But one thing that folks are often confused about at first is whether they need an extra level at all. And so I want to talk about that in just a second after I answer this question. Previous page, okay.
So, sorry.
Oh, the notation page?
Yeah.
Okay.
You said there's an empty 2-level model. So what about a 3-level model is the same?
A 3-level model would pick up an additional subscript because you'd have one for 1, 2, and 3. Beta 0 would stay the same because this is a fixed effect. It doesn't have subscripts because it doesn't vary. I would pick up another kind of U, essentially. So in my textbook, when I got to 3-level models, I was like, well, what comes after U? V does. And so I put V as level 3, but then I went back and used V for something else like 3 chapters earlier, and it's like, oh, oops. So I had V. You could have, basically the subscripts are what tell you what level it's at. So this one would have to become like OC something to be level 2, and then you'd have another one that's just U00, and then whatever level 3 means.
Well, on that note, do some people put like the first, like a 1 saying this is my first level or my second level or whatever, and then a use of 2 to indicate another level that you're working with? Or do they always typically just use a different variable?
It's usually variable, but the notation is author specific
Author-specific.
always.
Okay.
Especially in multivariate analyses when you're trying to keep track of not only what effect it is on what predictor, but then on what outcome. This notation is going to get more complicated because the fixed effects are going to be represented at level 2, and there will be placeholders down here for things. So this system will look different when we start getting into stuff. And I think it'll be easier to understand once you see like more examples of how the subscripts shake out. Yep. Okay, other questions? No, you're just waving at me? No? All right, back to my sales pitch. Okay, so when do you need a level? Think about a classic treatment design where you assign people to a control group or a treatment group. People are nested in groups. But you don't need a multi-level model unless there's group variability left over relative to the fixed effects. So if I only have one control group and one treatment group, once I put in a binary predictor for which group you were in, group is done. You've explained, allowed, all the differences across groups. Now, what if I had a randomized, like, multiple site trial where I have, say, 10 control sites and 10 treatment sites? Do I need a level then? What do you think? Big nod? You say yes?
I would say yes, at least to the point of making sure that they were not acting in the same manner. If you found that they're acting in the same manner, then maybe you could drop that level.
Yeah, potentially. So you would still want to put in a binary variable as to which kind of group you were in. And if all of your sites were equally good at administering the treatment and didn't matter which one they went to, then that would show up basically as that level of variance going down to nothing. And you could potentially take out that variance term, but it would have to be an empirical question. Yeah. So in that case, assuming that the sites are not all perfectly in line, it would still, if it still matters which one you went to, then that's still a group as a level. Now, would it be a good idea to design a treatment study with only 10 control sites and 10 treatment sites? What do you think of that idea? What if I told you each site was going to recruit 1 million people? Does that help? It doesn't. Because for those 1 million people, whether they're in treatment or control, is the same. It's not a variable, it's constant. So in terms of power planning, the power to detect the effects of your predictors depends on the level at which they're measured. And I've written grant proposals, analysis plans, where people were like, I have 5 treatment schools and 5 control schools. Can you do my power? And I'm like, you have no power. But I have 30,000 students. They're irrelevant because you're working at the school level in terms of what is control versus treatment. It's a constant across the students. Therefore, you can't explain why some students differ from each other because that's not it. They're all in the treatment group or the control group. So they didn't like that answer. But that's what happens. So that's one thing to keep in mind is that even if you can treat something as a level, it may not go well because there's just not enough information. It's hard to get a lot of clusters. Like Vladimir's project, you have 50 states, right, at level 3?
Yes.
That's all you're going to have. Like, there's no point in doing a power analysis because it's not like that can change. And how is that going? Are you able to estimate everything really well? No.
Not really.
Not really, no. It's not your fault, it's the 50 states' fault, but that's the thing to keep in mind. That what can be done is different from what actually could be done on the ground, like what's possible. All right, so where does dependency come from? We're going to talk about basically 2 main sources in this class. Mean differences across sampling units. So if some clusters are just higher on average on your outcome than others, that creates a constant source of dependency across the people from that cluster. So they're being treated as exchangeable. Like there's no differences across the people other than just the fact that they're from this cluster and that's all we need to know. That is going to be represented by this random intercept idea. So that's the U0 in particular. Cluster differences and the slopes of person predictors is another reason. So this introduces non-constant dependency. So some people's scores on the outcome are going to be more related based on their scores on a predictor. Like it's a different type of correlation pattern, and that is going to be represented by what is known as a random slope. So if a fixed slope means everybody gets the same number, what does a random slope mean? Want to guess?
Depending on who you are, you get a different slope.
You get a different slopes for different folks, essentially. In this case, it is the slope of a person-level predictor varying randomly across clusters. So each cluster would get a different version of the slope. So random means it's a variable. Fixed means it's a constant. So a random slope is a brand new concept. If you haven't seen multi-level before, you probably haven't seen random slopes before. In these models, I just want to put a plug for a set of models that is increasingly being developed, and they're really cool. There's other ways that you can ask questions about heterogeneity of variance. So for instance, are some classrooms more homogeneous than others in their achievement? Is there greater equity in some places? If you work at a company, are some supervisors, do their employees disagree more on their performance? Like if you're rating your supervisor, some groups might have a lot of agreement as to how they think their supervisor's doing, and some groups may disagree wildly amongst themselves. So in a lot of team and organizational type research, there's questions about levels of agreement of people from the same cluster. And so you can actually enter into these models, they're called location scale mixed effects models. You can enter into them predictors for the amount of variability and let that vary across teams or clusters or even people. So that's a whole nother level of models we're not going to get to, but I just want you to know they're out there. So if you have questions about variability. Now, why do we care? Why do we care about the patterns of dependency? No one wrote that as a research question, right? Like that's not ever going to be aim one of your grant, is to figure out the patterns of dependency in your outcome. But it is something that's necessary in order to get the answers right for the things that we care about. So what happens if we have the wrong model? Well, then we have the wrong conclusions. It's that simple. In your textbook and in many other places, when they talk about this problem, they say the estimates of the slopes will be okay. They are incorrect. They are smushed. That is a vocabulary word you will learn throughout this semester, a smushed effect. That happens when you put in your model one slope for a variable that's measured per person and ignore the fact that it's also likely to vary across your clusters. So when you ignore the impact of a cluster on a relationship, then that will lead to a distorted estimate for that slope. So that happens by default in single level models. Standard errors are going to be wrong to some degree. And whether they're too little or too big depends on the level of the model and what variables should have been there. But they'll be wrong to some degree. And the other piece of it is that what kind of variance you have logically dictates what your predictors have to do. So if you have between cluster variation, if some of your schools are better off than other schools, for instance, then you would need between school predictors to capture that. Why are some schools doing better? What is it about their staffing or their training or their programs or something that is a school level variable that would explain that? If you have within school variance, of course you do. If kids differ from each other, why is that? Well, then you need kid predictors. You need whatever demographic variables or home life variables or personality variables or whatever you're studying. They need to be kid things to explain why some kids differ from each other. If you were fitting a design like my friend Larry where you had item variance, if the words differed from each other in how their average response times shook out, why is that? Why were some words harder to answer than others? It could be predicted by word characteristics, like how long it was, or how semantic neighborhood it was, like how many other words are related to it. So knowing how much variability you have of each kind is a logical prerequisite for then setting up your model to explain that kind of variability. So if I have no variability at the school level, that means school level predictors basically have nothing to do. That would be a bummer if all of your hypotheses were about school level variables, for instance. True story, when I taught multi-level models at Penn State as a postdoc, I had a student there who was going to be the first person in his area in his dissertation to examine longitudinal change in some kind of variable. He was very excited about it. Time within person was his context. And the very first assignment was to figure out essentially how much variance was at the level 2 versus the level 1. We'll talk about that. And he found out that all his variance was at level 2. There was no change. Even though he had repeated measures data, the people functionally answered the question the exact same way all the time. So he had no time variance, therefore there was nothing that time level predictors could do. And I don't know what happened to him because he dropped the class shortly after we had this conversation, because I'm like, dude, you don't have longitudinal data, like this is your proof. And I felt bad about that for a little bit, but now I don't. I don't at all. It's not my fault that he had no longitudinal data, but why I don't feel bad is that we had this conversation at the end of January and not in May during his dissertation defense. Right? He's going to have to pivot, and knowing that ahead of time before you're like, why isn't anything working? That's a very bad place to be. So knowing what kind of variance you have logically dictates what happens next. That's the point of the story here. And in Larry's case, do you know why his people predictors were significant, but his item predictors weren't? Because he had like 200 undergraduates in his sample and like 10 words. So you can't predict differences across words if you only have 10 with much power. So thinking about sampling level, variability, and sampling size is a more complex task in these models. All right, so if you're like, do I have to? The answer may be no. In some disciplines, random effects models are considered bad and should not be used. And instead, you should be using something called a fixed effects model. What that entails is essentially putting in your cluster ID as a categorical predictor into the model for the means. So if I had 10 clusters, I would put in 9 binary contrasts to differentiate among the 10, treating it as a grouping variable. If I only had 10 clusters and I don't care about them, I just need to solve that problem of dependency, then that might be a fine thing to do. But if I care about why the clusters differ from each other, this is not going to allow me to answer those questions. So the other option then is to represent cluster differences as random effects. So that U0 term is essentially like a main effective cluster, but it's a variance in the model, not a series of fixed effects. Then we can see how much the variance across clusters is reduced after we put in cluster information. So it depends on sample size. Like if you don't have very many, it's hard to estimate a variance across very few units. It's not going to go well. That might be one reason to do it this way. Another would be that you actually care about the specific units of interest. So if I'm doing, let's say I'm doing a study at the university level, and I want to be able to talk about how student outcomes are in the College of Education, and in the College of Engineering, and in liberal arts and sciences. I might treat college as a fixed effect so that I can say, here's what happened in this college, here's what happened in that college, and I can actually differentiate because the deans of those colleges want to know about their college. They don't want to know, why do some colleges do better at this than others? That's a different question. If you want to know why, and you want to put in not just which college it is, but characteristics of the college, then that's a random effects approach. So there are, on your reading list, let me just point that out, there's 2 papers that have to do with how, let's see here, where is it? How this has been approached. So there is fixed effects and versus random effects in here, as well as this is a survey of all the different ways you can control for clustering. In terms of fixed effects, random effects, and cluster-corrected standard errors. So there are other choices out there. I'm going to just talk about random effects for the most part this semester because that allows us to answer research questions about the clustering, not just control for it and deal with it. Okay, how are we doing, folks? Can I get a thumb check? Reasonably? Yeah, remember, it's a continuous scale. You don't have to... All right, reasonably okay then. The last couple slides are more for longitudinal, but I figured I'd just throw them in anyway. So you can test any kind of predictor that you want in these models at any kind of level that you want. If you had something like repeated measures ANOVA, you wouldn't be able to have time repeated measures things that aren't conditions, for instance. That's like a software limitation. So being able to put in whatever kind of predictor you want at whatever level and any interactions that you want within levels or across levels is one of the benefits of these models. And then also the idea of missing data. So in longitudinal data, repeated measures ANOVA would take a data set and use this, and that means the person who's missing time 3 here wouldn't be included in any of the spots. But if you put it into multi-level software using a different type of data structure called long or stacked, this is how cluster data are naturally stored, then you would be able to use the 3 rows for the person that are complete. So the rule about missing data in these models is that every row of your data set has to be complete for that row to be included, whether it's a predictor or an outcome. You don't have to have the same number of people per cluster, but the information has to be complete to be used. And if it's missing, then you have to deal with that another way, and that's not this class. Right, Erica? Oh, yeah, Vladimir was in there too. Is it good to have missing data? Is that the take-home message? No, don't have it. That's the solution, especially for multi-level designs. Yep, yeah, it's a whole thing. How to deal with multi-level designs with missing data. In this class, the software that we're going to use will kick out the cases that are incomplete. So that's just what's going to happen. If there's a lot of cases, that's not a good strategy. And then the last part of the sales pitch is that a lot of what you already know is coming back into play, just an order of complexity higher. So this is the audience participation portion of the program. What's an intercept? Who's feeling brave? It's not a trick, I swear. Oh wait, what's an intercept?
I guess that's the slope, which is the mean of. I remember from the last course.
Yep.
That's beta 0, right?
Beta 0 is the notation for a fixed intercept. Yep. What's it mean?
That's it's not the slope. It's the mean, I guess.
The mean. Keep talking.
Yeah, the mean of the mean of the variables that's going to define that across all the data, everyone is going to get the mean number of the value.
That would be true in an empty model, but once you throw in predictors, how does it change? You can phone a friend too if you want.
Michael.
Okay, he's phoned you.
That is when you have a 0 value inputted for all your other predictors.
Yep. Expected y when all the x's are 0. Expected outcome when all your predictors are 0. Guess what? It's still going to be that this semester.
Okay.
The definition holds. The only twist is that rather than having an intercept, we have a random one by which each cluster gets a different starting point for when all their predictors are 0. But it's the same idea. If I told you the slope of a continuous variable was 3, what's that mean? Fixed slope.
When the variable go up by 1, then the outcome will go up by 3.
Exactly right. When the predictor goes up by 1, the outcome will go up by 3. That's going to be the same thing in this class too. However, it might be the case that it goes up by 3 in one cluster, but up by 4 in another cluster, or up by only 1 in a third cluster.
That would be our random slope.
That's a random slope, yep.
Okay.
The extent of the slope can vary across clusters for people-level predictors. So let's see, I'm trying to come up with, I'm calling on you again, Vladimir. So your project, they're interested in gender differences of college applicants.
Yes.
So men versus women at level 1, and they have multiple years of data in every state.
Yes.
Yep. So the idea at level 1 is a gender gap as the construct of interest. And the study's wanting to know how that changes over time and how that varies across states and what moderates those differences. So a level 1 slope can vary randomly over level 2 things and over level 3 things. Yep. How about a categorical variable? If I told you that x is binary and the slope is 3, does that change your answer any? It's a group difference, yeah. As x goes up by 1, meaning as you go from the 0 group to the 1 group, your outcome would go up by 3. So the words change a little, but it's still a 1 unit change. It's just that's the full scale of the variable. Last but not least, what's variance?
Random slopes.
If the slope varies across clusters, then it has variance, yes. I'll accept gestures. Like just conceptually, how would you describe variance to somebody who's not familiar with this?
Spread of your data.
Yeah, spread, right? Like if you have a group of data, is it like this or is it like this? That's the same thing. That hasn't changed. Variance is error. Did you know that? That was a thing yesterday. I
Squared
heard.
errors, but yeah.
Well, no, this was an epiphany I had my first year of grad school. So I was fortunate enough to take, I had 6 different undergrad courses in statistics and research methods because I took the 3 undergrad courses at the University of Nebraska and then I took the graduate sequence my last year. So I had a lot of training. But I didn't realize that variance was error. Until I read it in a book. And then things just sort of fell into place in a way that they never had before because I had taken, research design where you're talking about your experiment and your ANOVA and you have your between subjects error and your within subjects error, and error is bad because you screwed up your experiment. Why didn't everybody do the same thing in the same way, right? Error is bad and you want to reduce error through designs and controls. And then I took a regression class where variability was individual differences, and it was good and interesting, and we have to have individual differences, and we don't have anything to do in our research otherwise if I don't have differences. So if variance is error, then it's neither good nor bad, it simply is what it is. And so that's where we get into hills I will die on in the field of multi-level modeling with respect to R square. In the U's, let me go back to the equation, there are some folks that would look at this and say, the variability attributed to U here has explained, X% of the variance in Y. They would add this to a model and talk about the variance that it explained. But that to me makes 0 sense because U is a source of error. You're allowing each cluster to have a different mean. So you know that they have a higher mean or a lower mean, but you don't know why. Error, as unexplained. Likewise, you know that kids from the same cluster still differ from each other. You don't know why. That's also error. And if I go up a higher level, right, I don't know why some items differ from each other. I don't know why some people differ. I don't know why some years are different. I don't know why some schools are different, or districts, or da-da-da-da-da. You get the point, right? These are all different kinds of error. But adding terms to the model for the variance to split them into their respective parts does not explain that error. It just says what it's allocated to. So I could say that 30% of the variance in this outcome is attributable to cluster differences. Attributable to means I don't know why, but it's something about the cluster. That to me is not a semantic distinction. I like that better. But whether or not to include random effects in effect size measures is somewhat controversial. But variance is error. So the tricky part then for us is trying to figure out how many kinds of error we have, and for a given effect in the model, which one it's supposed to explain. There are rules for this and there are algorithms for this, and sometimes they break. You will see variances go up instead of down. It happens.
Cool.
Yeah. So then R square is just like 0-ish because it went the wrong way. It would go negative. Question?
Does it happen that when you start your project, you thought from theory that meaningful group is like maybe 2 or 3, and then as you proceed the project, it turns out that maybe we have to add another group, we have to create
Another level?
Yeah. Does it happen often?
Yes. So the question was, I'll repeat for the recording, is it the case that you find yourself needing to add additional levels relative to what you expected? Yes. but you'd have to know why. Like, you'd have to go looking for it. I don't know of any useful diagnostics that would find sources of dependency that are, like, you don't know why they're there, like, you try and figure that out. But if you think about your sampling design, anytime you have people from a naturally intact group, that's when you would need to worry about it. Or when the group is a consequence of something that could matter. So undergraduate research data. Undergraduates are really, really happy to be doing research for class credit in psychology, I'm sure. That hasn't changed, right? That's the one constant.
Or requirement because of what you're.
Yep, and then as you get older in your undergraduate career in psychology, if you want to go to grad school, you have to work in somebody's lab, which means you pay tuition for the privilege of working. Right? Are we still doing that too? Yep.
Isn't that some of our TAs?
Uh-huh. And some of the TAs at the graduate level are paying tuition for the privilege of working. Right, Erica? How many classes are you TAing that you're paying for this semester? Only two. And how many are you TAing for money? One. Okay, so she's all-time TA right now, so she can finish her college teaching certificate. But yeah, where I was going with this, are all undergraduate lab participants equally diligent and responsible? And are they going to follow your protocol exactly the same? No. So could you have differences that you need a level for due to which RA ran the study, ran that group? Yep. I mean, those are sources of differences you wouldn't plan on, but happened. I helped with a project where there was different tutors for students, and the pattern of results was completely backwards for two of the tutors, in terms of just what happened. And, okay, but clearly we need to control for tutor. There's only two, so I don't know what happened, but that would be a question, in the future, as to why did these two people have such disparate outcomes? What did they do differently? So, yes, the answer to your question is yes. It also works out the other way. Sometimes you expect to have differences and they're not there. The higher up you go, the less likely it is that there's going to be a strong source of dependency. The math scores of kids from the same class are related. The math scores of the same, classes from the same school, maybe. Schools from the same district from the same state. By the time you get up there, I don't know that there's a lot of math performance differences across states, Where that could go awry, though, is if the information is subjective. So if I have a teacher who's filling out a form about each of their students and how aggressive they are, that will introduce probably more dependency because one person is providing their opinion for the 20 kids relative to the 20 kids doing their own individual thing. So it depends. If you don't have variance, though, then you're not going to have a lot of success predicting it. So that's one thing. But you can't really control that unless you're deliberately changing your sampling plan to try to increase variability, for instance. The end. So you already know how, or you will soon. That's where I wanted to land on here. So multi-level. How are we feeling about this? Okay? Okay? Should we talk about some level 2 predictors and notation and stuff? Why not? Let me start a different video.